Hello, my name is Valentin Koch and I'm a PhD student at Helmholtz Center in Munich. I'm happy to present you our paper that was accepted at MICCAI 2022, Noise Transfer for Unsupervised Domain Adaptation of Retinal OCT Images. We addressed the domain shift problem for semantic segmentation of retinal OCT images. Domain shifts are generally distribution shifts, which here are caused by the use of different imaging devices from different manufacturers. Each device produces images with domain-specific characteristics, such as noise or brightness levels. When we train a segmentation network on images of one domain and test it on another so-called target domain, the performance will generally be bad. The core principle of our suggested algorithm is to restyle images from the source domain, where we have ground truth segmentation labels, to match the characteristics of the target domain images. We then train the segmentation network with the original images and their segmentation maps, as well as with the restyled images and the segmentation maps. This allows us to train a model that works well on both the source and the target domain. It is also not restricted to just one target domain, but can be used to adapt to multiple ones at the same time. However, this idea is not new. Our key contribution is the way we achieve this style transfer. During training, first of all, we randomly pair images from source domain and target domain. We then write both source and target domain images as their respective singular value decomposition U sigma V transposed. To achieve style transfer, we then use the first k singular values and their corresponding right and left singular vectors from the source image, where the content of an image is encoded, and add the noise that is encoded in the k+1 up to n singular values and their corresponding vectors from the target image. So the idea basically is to keep the content from the source image while adapting to the noise pattern from the target image. After this operation, it might happen that some pixel values are smaller than 0 or larger than 255. This is why we clip the resulting values to the interval 0 to 255. To not only account for noise, but also to match the pixel intensity distribution, a histogram matching step is done in the end. Let's look at some results. Here we can see how we achieve style transfer from one single image from the source domain on the bottom to 3 images of different target domains on the top. In this UMAP, we used 3 different noise estimation measures to measure noise of images from different domains before and after SVDNA restyling. We can see that after SVDNA, the dataset's noise characteristics align well, except for the very noisy bioptogen domain. We evaluate our method on a dataset from the retouch challenge. We compare SVDNA to a cycle-GAN approach that was previously suggested to achieve style transfer and improve segmentation performance for retinal OCT images, as well as confidence regularized self-training and Fourier domain adaptation, which were both successful on popular domain adaptation benchmarks. Therefore, we did a 5-fold cross-validation on the test set, where we used 80% of the data, depending on the method, as either style targets or unsupervised training data, and evaluated on the remaining 20%. As the baseline, we use a model that is trained on images from the source domain without any domain adaptation techniques. We can see that while all methods improve over the baseline, SVDNA performs best. I want to thank everyone involved, namely Olle Holmberg and Hanna Spitzer from Helmholtz Munich, Johannes Schiefelbein, Ben Asani and Michael Hafner from the Ludwig-Maximilian University, and Fabian Theis from Helmholtz Munich. I also want to thank my advisor Carsten Mahr for his support. To summarize, we propose a simple style transfer method to overcome the domain gap for semantic segmentation of retinal OCT images. SVDNA does not need any training and can be used in a few lines of code in any training pipeline. The code is publicly available on GitHub.